This episode on new developments in countermeasures for drone warfare, specifically directed energy countermeasures, is a departure from our usual programming on School of War for a few reasons. For one thing, the conversation is more technical than we usually get. And for another, instead of a military historian or policy analyst, our guest today is an industry leader and also a veteran with an engineering background who's currently the CEO of EPIRUS, a firm active in the defense directed energy space. I think it's a really interesting conversation going into the details of how a particular and central aspect of combat is evolving as we speak, with some useful speculation on how tomorrow's countermeasures will themselves provoke countermeasures of their own in the continuing cat and mouse game of battlefield innovation. Let's get into it.
It is a prescription for war, this Iraqi invasion of Kuwait.
December 7th, 1941, a date which will live in infamy.
The bloody experience of Vietnam is to end in a stalemate.
We continue to face a grave situation in Iran.
The people who knock these buildings down will hear all of us soon.
We shall fight on the beaches, we shall fight on the landing grounds, we shall fight in the fields and in the streets. We shall never surrender.
For maps, videos, and images, follow us on Instagram, and also feel free to follow me on Twitter at Aaron B. McLean. Hi, I'm Aaron McLean. Thanks for joining School of War. I am delighted to be joined today by Andy Lowery. He is the Chief Executive Officer of EPIRUS, a defense company that is doing some interesting things with countermeasures for drones. This is actually exciting for the podcast. It's the first time we've had an industry leader as opposed to a historian or a strategist or a political leader on the show. So, Andy, I'm delighted for you making the time.
Yeah, thank you very much for having me, and I'm proud to be the first industry leader. So, thank you very much for the invitation.
You have an interesting background, and let's start there if you don't mind. How does one end up as the chief executive officer of a company like EPIRUS? How did your career go before this?
Well, I had three kind of 10-year sort of active duty military, then to industry, and then to startups. And my first 10 years, I started out first enlisted and then as an officer in the Navy nuclear propulsion community, where I was qualified on subs and surface ships to operate the nuclear reactors. My active duty career culminated on the John C. Stennis as the reactor electrical assistant on board that ship. And then I went to reserve duty and completed sort of a 20-year career and retired in 2017 out of the Navy. And then when I, in 2002, moved into kind of the industry, I started where I kind of focused my college education, and that was on microwaves, big topic of today's discussions. And whilst in college, I sort of got a love for RF and waves and all things of waves, and I was able to kind of not work too much, obviously, on the nuclear side in the RF and microwave department on the nuclear reactors. But when I got out, I ended up joining MACOM, which is a RF power amplifier company, one that we partner with here at EPIRUS actually today. And for a number of years, I was the first of business development and operations. And eventually I was a general manager of a facility in Torrance, California that did high powered amplifiers, that kind of some of the stuff that we have in our system today that I'll talk a little bit about. And then my last 10 years, I took sort of another detour after I got done. I should say that after MACOM, I spent a little less than a decade at Raytheon. And so at Raytheon, I was a chief engineer, and I was privileged to kind of be the head guy on some very large areas. At first, a big space area programs, and then intelligence, surveillance, reconnaissance for a while. And then eventually, I was put in charge of Next Generation Jammer, a Navy electronic attack program back in 2011, 12, 13, in that time frame. Raytheon ended up winning that competition, and we went on to kind of have a pretty sizable electronic warfare portfolio that I ended up being the chief engineer over. And after that, I spent 10 years in startups, and that's kind of getting close to where I'm at now. I had two other startups before this. Both of them were more on the commercial side, looking at sort of work tools like wearable computers and augmented reality to assist industry. I had two startups in that area. I just kind of stepped down a few years ago from my second one called RealWare. And I joined EPIRUS as sort of, employee, maybe around employee 100 or something around that time. So it wasn't really a founder, wasn't in the early days. But some of the folks that did found the company, like Dr. Bo Maher, he worked for me at Raytheon. The founding CEO, Nathan Mintz, worked for me at Raytheon. So we had sort of a league there when we were at Raytheon. And so when they saw the company really starting to grow and expand, they asked me to join about 2.5 years ago. So I got pulled in sort of in the later stage, but I've been having a lot of fun. My last two startups were more early stage to kind of a medium stage. This one's going from medium to hopefully into growth stage as things start to kind of pan out for us over the next couple of years.
Well, my military background is in the infantry, so I know you'll slow things down. If we need to illustrate things in crayons, you'll help me out on that.
I'll compare everything to bullets.
Perfect. Well, so speaking of bullets, so I want to get to the main system that I think the main system that your company is working on, which is this countermeasure system for drones. But let's take the following route to get there. If you don't mind, talk a bit about the battlefield today. We all know that the battlefield is full of drones. We've talked about it a bit on the show, but we haven't really devoted an episode to it. But we see that, in the Red Sea, targeting shipping. We've obviously seen it recently in assaults on Israel, and we see it on the battlefield in Ukraine. What are the problems that this evolution or this rise to prominence of the drone as a weapon of war and a continuing, ISR platform as well? What are the problems that this presents to military forces that are new and that you are working on solving?
Yeah, it's a great question. And it's really sort of profound, I guess, what we used to call even a decade ago, asymmetrical warfare, sort of like this isn't the normal warfare that we're used to dealing with. And now it's become sort of the primary mode of warfare, as you see developing out in Ukraine and now in Israel. So I think what has happened, and I think there was sort of an indication or a nod towards it when you look at the IED problem in the early 2000s, 2006, 7, 8, where we had improvised explosive device being kind of rigged up by, the proverbial Radio Shack crafty guy or lady that would go out and figure out how to use sort of available electronics in order to create some sort of a weapon. And you see that sort of becoming the hallmark, if you will, of the whole consumer movement. Usually it was defense that had the best stuff, and then we would eventually trickle those ideas and those technologies out to consumer land. But since the advent of internet and computer, it seems that very distributed systems, ones that don't have a centralized command and control, which was traditionally, I think, the way that we kind of geared up for the big fight. Now it's become a very distributed sort of command and control architecture where you can leverage little simple gadgets and things like that and create sort of a new warfare paradigm where it's very hard. They're very evasive. They kind of sneak underneath our radars, so to speak, and they're very hard to detect, but they can create these days immense damage to these bigger sort of jackhammer systems. We've got these swarms of things, proverbially, metaphorically, and literally swarms of things that are beginning to become really, I think, the new way war is going to be fought, for here and forever. And there's a lot of talk and rhetoric that warfare, as it's been now expressed with USVs and most importantly, the air vehicles, the UAVs, as you start to look at what's going on with the attack at Tower 22, where unfortunately we lost a few lives to some soldiers over there, injured, I think up to 80 folks are pretty significantly injured from just one drone, as far as I understand, kind of having a very sort of interesting strike. We sort of took our back on our heels a little bit starting at the beginning of the year. And I hear this among our customers, among some of the politicians, where we no longer can assert that we are in control of the entire airspace, at least when we look at the short range air picture, that short range, maybe out to 10 to 15 kilometers, up to 1,000 feet. Within that airspace, I don't think anyone is saying we maintain a pleasant air dominance over that any longer. So these things have been able to sneak into our sort of highly structured C2 kind of, command and control hierarchical systems. They've been able to sneak under those systems and be able to exploit the weaknesses of them in a very, very cheap way. So this is pretty interesting to understand, because a lot of people call it a problem with the cost equation because they say, well, we're using consumer electronics to defeat these very sophisticated military systems. But when I talk to others in Washington and whatnot, the real concerns around arsenal depletion over cost equation, where the strategy, as you saw in Israel just recently, is to throw a bunch of junk, through the air, require us to kind of combat that with our sophisticated, expensive systems, but they only have so much magazine depth, to go back to, I said, everything to bullets, right? So we only have so much magazine depth in those sort of arsenals of kinetics, and we can throw a bunch of pipe bombs that are kind of ballistic missiles. We can throw a bunch of drones that are just repurposing, computer laptop factories and whatnot to create these things. And we can just flood the air with these things, just completely flood the air. And the US won't have any possibility to have a deep enough arsenal to beat it all. And so once we deplete all of the kinetics that the arsenal has in it, we can send our real missiles in to do the damage that we really want to do. It's a real strategy that's being thought about in Iran and China and Russia. There's a real strategy that we need to consider. And I think there's two ways of approaching it. One, we see the replicator program that you may be familiar with, or your audience may be, where we're trying to kind of Me Too that a bit. Like, how can we keep up with this type of movement and this new type of asymmetrical warfare? But then on the flip side of it, you've got ideas like EPIRUS, where we're saying, well, no, let's use our strengths to try to, go move 2 moves ahead, not go to Me Too and follow up with replicator, but let's use a system that can spread energy across large volumes of the atmosphere in order to hit all of these things. And so that for a very low cost, but more importantly, no arsenal depletion, we can take out the junk, we can take out the toys, we can take out the group 1s and 2s, and even a lot of the higher level drones, because they're built very, very consumer electronic-esque, if you know what I mean. And so with that sort of an idea, we can reestablish dominance. Not only can we go Me Too and meet them in the middle and say, all right, now we're having drone on drone fights everywhere you see, we can instead say, let's make a more sophisticated approach. And that's what the one that EPIRUS and with their customer, the Army right now, Army Richto, we're embarking down this path of exploring basically just that.
Yeah, there's a way in which your success actually spells real problems for the Me Too option, right? Because your success presumably is then imitated by competitors, and that leads us to places we can kind of reason through and try to think what the world looks like a few years down the line. Let's just stay with the world as it is for just one more second, if you would. Going through TBS some time ago, low altitude air defense was not a sexy field. It was not a thing that anyone really wanted to be involved in, and clearly today it is at the center of what's important on the battlefield. You talk about these expensive countermeasures that exist today and sort of sending projectiles to hit a projectile. What about electronic warfare as it exists kind of in its current or recent mode? What role does that have to play in all of this? Not as directed energy, but more in the sense of jamming and interference with command and control platforms. Why does that not fully get the job done in terms of a countermeasure?
Yeah, it's not. I mean, all of these ideas, even kinetics, I don't intend to kind of throw out any of the babies with the bathwater. And, the military will say again and again, this is a layered defense problem. And sometimes people think of the short range air picture as one layer, and that's a misnomer. That's a bad idea. I mean, there's many things going on in there. It isn't just like one type of vector that we're trying to kind of oppose within 10 kilometers. There's like ISR, group 1, group 2s, there's swarms of group 1s, group 2s, there's the old group 3s, like the poor man ballistic or poor man cruise missile type stuff coming in. So you've got a whole bunch going on there that I think you almost have to look at even that 10 kilometers as a number of layers. And in fact, when we talk to the Army, we talk about things like serial killers and not like in the old traditional way you might think of it. Serial killer meaning one at a time. You look at one bullet, one drone, one laser, one drone, and you have, or one drone, with some of the kinetic drone on drone type stuff. Whereas this system kind of, and I don't really mean even EPIRUS, let's talk in generality, because Raytheon could produce a system like this, Northrop could produce a system like this as time goes on, and to create sort of a element of electronic warfare high-powered, though, electronic warfare. So I'd almost categorize our version of directed energy under sort of the superset of different electronic warfares, ranging from cyber to kind of your traditional jamming and getting on signal, all the way up into what we're doing, which is like basically penetrating directly into the analog circuits. And that's the big difference. It looks very similar to a jam or to some kind of an electronic warfare attack, but we're not using the traditional vector going through a receiver, through an antenna, into the digitization of it, and then re-analog it and go do some sort of an effect. We're going straight into the analog pieces, the ones that have voltages and switches and op amps and things. And by getting right in there and then having sophistication to what we do when we're in there by waveform agility and all the rest, we can basically concoct or sort of deduce ways of doing almost what would be akin to sort of an analog cyber attack. And it's not stoppable by traditional ways. So if we look at your question, I know I remember it still. I know I'm going on a little bit of a rabbit hole, but the question was, what about electronic warfare in the traditional sense? I think that is a layer. I mean, for sure, you want to have some basic electronic warfare, barrage jamming, other kinds of techniques that you can jam. The issue is that it's very, today, what's being applied to this fight is very unsophisticated. Like when you compare it to the electronic attack, a next generation jammer, it's a very unsophisticated set of electronic warfare systems that are being out there that when we know about the cat and mouse game that can be played, they can be a lot of times easily spoofed or defeated. They can be defeated by jumping frequencies between different frequencies very quickly, by encrypting the signal, or just going offline where you're flying by waypoints or inertial navigation or whatnot. And if you just don't deep connection, you're not taking anything in. And as sort of the real true autonomy of drone flights begin to emerge, which I don't think it's there today yet, I don't think you see anything that's truly autonomous in the drone categories of flying to waypoints or flying on some sort of electronic wire of some sort, whether it be a link or whatnot, you know what I'm saying, versus true kind of thinking autonomy. But it's around the corner. That autonomy is around the corner. And if you're able to drive to that kind of autonomy, you can be virtually self-contained, where you're not talking to the outside world at all. And thereby jamming would be more or less useless if you're not taking anything in. Now, I don't think that we're there yet. And I think jamming still has a place on the battlefield. I think we need to look at advancing the way we're jamming and what we're looking at and bringing in sort of the knowledge that comes from programs like Next Generation Jammer and what we do there, and applying that to this short range air picture fight. But then on top of that, again, lasers, hey, let's keep pursuing that. That looks good. That looks like that's an effective weapon. Looking at different kinetics options, keep pursuing it. Looking at the different drone on drone stuff, let's keep fighting it. Because this is serious. This isn't a competition of like, hey, who's going to make all the money? This is a competition of reestablishing our sort of airspace superiority and dominance, and being able to ensure our warfighters aren't going to be killed or injured in large numbers as these battles and these fights begin to break out. So I think it's a team effort, and we should all kind of come together as a team in order to figure out the best solutions for these emerging and greatly ballooning problems. By the way, it's like it goes from a small little number of things to like this huge cloud of enormous amount of activity. And that's another area where this consumer electronics go to warfare is really sort of got a special sort of flavor to it. A military program doesn't scale like some of these consumer electronics weapon system programs do, where just overnight, everyone is kind of going out and doing some sort of a trend of some sort of a new way of attacking.
So this is probably an oversimplification, but do you agree with the following characterization that autonomy is a kind of answer to the existing electronic warfare countermeasures that exist, and then microwave is an answer to the autonomy? Is that a fair crystallization?
That's very fair. That's very fair. And there's ways of defeating even the high because these are basically putting huge electromagnetic interference fields out there that are sophisticated, like I was saying earlier, and can do some smart stuff. But those, mechanical shielding of that sort of stuff is a way that you can try to defeat these large EMI fields. Like you look at airplanes that fly up in the atmosphere that are engineered to prevent the EMI that's from solar storms and stuff from coming in and affecting your systems. But the problem is that consumer electronics and especially the group ones and twos just aren't built with any of those requirements in mind. And then to try to go back afterwards and put some tape around it or some copper tape or whatnot is just a complete disaster. Trust me. I mean, you can't do it that way. The penetrations break your Faraday cage. And actually what ends up happening is a lot of times that tape or those ways of doing a poor man's version of trying to do electromagnetic shielding actually worsens the problem for the drone provider because it creates a cage that's somewhat permeable. We can do our software defined back end in order to penetrate those cages. And then once in there, it stays in there. It doesn't come out as easily as well. So you can create a bigger problem by trying to defend against something like what we're doing in those low cost types of applications than you can when you just leave it alone and say, hey, let's try our best. And so it is a very difficult thing to harden against in this class of product. Very, very difficult thing. So I guess your statement is true, I would say, is that's a good way of looking at it.
So I have a microwave in my house. I used it to heat up some pizza yesterday. That's what I understand it to do. It heats up things in a box. Are you heating up things at a distance? Like, how does it actually work?
Yeah, that's a great question. So the microwaves in our house are continuous wave. They put out a constant wave of microwaves that are designed to have a high average to peak power ratio. So the high average power, and that average power creates sort of vibrational temperature that kind of are being induced on water molecules and whatnot. And then that vibrational temperature stills off into translational temperature and heats up your stuff. And then incidentally, if you were to create a microwave weapon against people, for example, you've heard some of this stuff, you'd want a high average power to peak power ratio so that you're having basically a continuous wave beam that's doing something similar to a person. Our system operates on a very high peak power to average power ratio. So our average power is very, very low compared to the peak power, but that peak power in the time frames that we're talking about, the pulse widths that we're talking about, actually does particularly disturb electronics. It makes it so the clock can't be sort of understood as it's trying to do different things. It's trying to execute various commands, basically drowns out the ability for the system to kind of talk to itself. So in effect, what we do with our type of microwave that we're putting out there is imagine if in the atmosphere you could put, 100 or 1,000 volts per meter. So over a 3 foot, if you had a little fluke, you measure across this 3 foot range and you've got 1,000 volts you're measuring. Now, if you kind of go down into sort of the microelectronics of switches and stuff, a lot of times the only way they get operated is by having a 1 volt, 2 volts across the switch. And that's what makes the switch. Now, if you can imagine that big voltage in the air just applying itself, as long as it can get absorbed and as long as it can get kind of taken in by the electronics of the drone or whatever you're trying to go after, then it can take those switches and whatnot and cause them to fail open or fail shut. And so it's more of an electromagnetic effect than a heating effect that we're doing. We're getting into the electronics themselves and causing disruption on how it operates, not so much an overheating like you described in your microwave.
And how does, maybe give some physical descriptions here as to how something like this can actually be deployed. I presume, and I've seen videos of the testing on a vehicle. Can we get down to backpacks, et cetera? And then second, but closely related question, how is an operator actually using this? Is this something that is aimed? Is it a series of items that are projecting across one another in a space? Like walk me through how this actually is used on a battlefield.
Yeah, okay. So the system, if you ever look at the system and if you have somewhat familiarity with defense systems, it looks like a large radar, like an L-band radar that you might see Lockheed Martin produce or something. It's got a square appearance to it, like a square rectangular appearance to it. It's about 10 foot by 10 foot. And I'm talking about the base defense system, the one we're working with the Army. Now, inside that base defense system that's on a trailer that can be trailered around and then positioned where it needs to be positioned and then points up into the sky, what it does is it operates in conjunction with sensor systems. And when the sensor systems detect a drone, it tells this system to say, hey, point itself over in this region of the sky. Now, it doesn't need to be right at the drone. It can just kind of get into the sector, and it points that rectangle out in the sector where it knows the drone might be coming. And then it takes over from a fire control system, says, okay, we know right where the drone is. Or in the case of our system, we know right where the swarm of drones is. Could be 10, could be 100, could be 1,000 drones. And it says, here's where all those tracks lie. And then what our system does is within a sector of about 1/6 of the sky, it can instantaneously scan the beam anywhere in that 60-degree by 60-degree swath. So in a second, we could put energy everywhere in there. So let's say there is a big, like 1,000 drones or whatnot in that 1/6 of the sky coming in. You could just command the system to say, take up that whole area and put a wall of energy. And then as those drones come into that wall of energy, each one of them will be affected by the same effect. It stops working. And then, of course, when a drone stops working, it falls up out of the sky and crashes onto the ground. So that's the basics of how the system's operated. It's connected into various systems, like one is Anduril's Lattice, is a C2 system that's out in the space now, but also FAD C2, which is a more traditional Army-owned system that Northrop Grumman does a lot of the programming on. The FAD C2 is a short-range kind of air coordination system that the soldiers actually interface into, and that's the screens that they're using. Both the sensors are getting kind of plugged into it, but then also the effectors are plugged into it. And they're using a very kind of almost video game looking screen to say, all right, we see this one, label it at hostile, label it hostile. And then it says, all right, point the beam to it. And then in the brains of the Leonidas system or this big effector system, it points it into that direction electronically. So it steers it electronically, much akin to like the new headlights with a lot of LEDs and they can turn around a corner. It can basically turn the beam and point it within a certain region at whatever sector it needs to point. And then they say, they give a weapons release command and they hit the button. And then it starts radiating this very, 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 very high peak power within a large kind of volume of space. And that's the basic way it operates. Internal to it are a lot of those, similar to that analogy I made about a headlight. There's a lot of hundreds of these LEDs, and we can make a big LED type of a light. You can think of it that way, and it would shine very long distances and protect things like air bases and such and whatnot. Or we can trim down and say, well, we only need 6 LEDs, let's say, on a little hand carryable one or a backpack carryable one, as you're asking about. And now that one's going to have a lot less range, just like a lot less brightness of a flashlight if you had a lot less LEDs inside of it. But depending on the application, if you can get close in within feet or tens of feet of something, sometimes a smaller form factor works out. In particular, I'll tell you one example of that. We are in June going out to this Antex event that the Navy sponsors, where we're going to take a smaller size system, only about 50 or so of these LED type elements that I'm talking about, which we call LRAMs, line replaceable amplifier modules. And that particular system works real well if you put it out on the nose of, let's say, a rip boat to take out outboard boat motors. So we're looking at a lot of not only UAVs, but USVs that are doing damage in Ukraine. But we also have things like pirate boats and drug boats and things of that nature. Wouldn't it be splendid if we could have something that just turns off the outboard boat motor when the energy's on it? But then if we decide, oh, no, it's a good guy after all, we can remove the energy and then the boat just starts back up again and goes on its way. That's the idea of actually putting one of these smaller systems on board a boat and then ruggedizing it to the sea and stuff.
That's fascinating. I don't think
boat motors. Yes, sir.
No, it's fascinating. I don't think I captured that obviously very important technical detail that when you hit something with this, you're not frying it forever. You're simply disrupting its current operations.
Correct.
So does that, just as a practical matter, is that, let's say I'm trucking along, I'm a drone, I'm at, 500 feet, kind of close to the earth, like, and you get me, just in terms of employment. So I start to fall out of the sky, right? Because my stuff doesn't work anymore. But as a matter of employment, can I fall below the beam? Like, and recover? Like, how do you work with that
Yeah,
part?
well, it doesn't, that is a great question. Not on the quadcopter types, it doesn't work very well. They start to tumble, there's no recovery.
Yeah.
They don't ever recover. But on the fixed wings, to your point of view, and especially the gasoline powered fixed wings and such, they can get some like propeller momentum, right? And if you knock them out for a little bit, but they fly from the beam, then they can maybe start up again. So you have to keep the beam on the target for as long as until you declare battle damage assessment complete. And the beam will do just that. It'll trace to the system. So as the drone or whatnot could be flying crisscross across their path, we don't just keep it there. We go with it and keep the beam shining on. Or if the boat motor's driving one way or another across their nose, we'll point the beam towards the boat and keep it on the boat the entire time until the effect has fully taken hold and it no longer has a chance to recover or whatnot. And then we'd move to the next one or the next one.
That's fascinating. So, I mean, it's interesting what the law enforcement applications could be depending on the effects on personnel. What effects, if any, does this have on personnel?
Well, we go through, it has a similar effect. If you stand as a high-powered radar, like a Spy-6 radar, if you stand next to the main beam, like if you're right there next to it, it could have a microwave effect on you, which would be hazardous. And most of the time, those aren't like give you cancer or anything, which some people think or might think. It's just heating you up. But that could be bad if it's heating up your insides, right? Yeah. So you don't want to get heated up. So we perform a series of tests. They're called, in the military, they're called HERO, HERP, and HERF. And they stand for hazards of electromagnetics against personnel, against weapons, or against fuel. And there's very, very well-established science around this on how to keep out zones and all the rest. And then around the actual, what we call side lobes and back lobe, where the operators will be sort of around the back of it, it's a very, very, very low level. So you can come in very, very close to the system and not have any risk of any sort of damage. But then out in front of it, if you're standing right in front of the system, that would be a bad idea. I wouldn't recommend that, nor would we allow that. Well, then within the beam, once the beam takes shape and gets out there in the field, it has very, very little to no effects on the actual people. It just is targeted and tuned for the electronics. And that's paramount to that peak power to average power discussion we had earlier, that we have a very large peak power of the system to get the range, but then that dissipates the average, and the average power is very low because we take a pulse and then take a rest and take a pulse and take a rest. And by doing it that way, it makes it still safe to be used in the law enforcement applications and whatnot at a certain range. And so there's a certain sort of minimum range that you'd want to be at.
I don't want to get too philosophical on you here, but I'm just hearing you lay this all out. I can't decide if what you're describing is just the sort of most newfangled thing. It's like Star Wars come to life. It's like a shield of sorts.
It is a bit.
So there's that way of looking at it. And then there's the other way of looking at it, which is you were the first to reference radar a little while ago. Thinking about the Battle of Britain and the way in which radar is introduced as the sort of battle-saving, for Britain, life-saving countermeasure of its day, because otherwise there's no way to coordinate the air defense against the Luftwaffe. And in a way, you're dealing with the least related technology. So it seems sort of incredibly sci-fi, but at the same time, something sort of familiar from, 1940.
Yeah, no, that's a poetic way of saying it for sure. I think I'll have to use those words you just said, because it's funny that I was talking to a fellow who was a real history buff and talked about how Winston Churchill back in the day kind of realized that no longer would naval power be the dominant sort of decider in war. And he, even though an old naval guy himself, shifted the whole government and country to go over to the Air Force and to make sure that they built a strong and robust Air Force. And it's similar to what you say about the radar as well, that there's certain technologies or moments in time where things have to pivot into a certain class of technology. And we believe at EPIRUS for sure, and I think I have a lot of customers and others saying the same thing now, that this is one of those new paradigms where we finally got to a point, and you say, well, what is it, Andy? What caused it to be? What flipped it over other than the need, other than the emerging need, the capability gap we've discovered. What's the technology thing that kind of flipped the bit? And it is really around a substance called gallium nitride. And it's a type of, say, like silicon. It used to be all silicon. We'd make amplifiers out, these transistors that amplify RF microwaves and whatnot. Today, we use substances called like gallium nitride. And gallium nitride is just this ingenious type of material that can produce massively high power density types of outcomes. Like it can just blows the lid off of old silicon, like literally blows the lid off of it. And over the last decade or two, let's say almost 15 years, gallium nitride is on this like terror of a run of just getting more and more capable, meaning more and more power dense. A lot of it is pulling the heat out of it, getting the heat out of it that it generates, making it more and more efficient. And we are specialists in controlling those very, very high-powered amplifiers. We've partnered with MACOM and developed some new types of technologies within the class of gallium nitride that lend themselves well to this particular application. But then we have a bunch of technology at EPIRUS that controls or contains that big King Kong of an amplifier. And that controlling those chains, if you will, if you think of it that way, to restrain King Kong is what EPIRUS is especially good at. That's our especially good IP on how to control this much energy and this much power. But now that we're doing it in solid state versus the traditional methods of directed energy, which were like microwave ovens with magnetrons and TWTs, we're doing it in solid state. And then that allows us the sophistication, flexibility about bringing our duty factors up, bringing our pulse widths much more wide, doing different things like that, different polarizations. We can configure the polarizations and go, I can keep going and listing like 10 things that we can change about the waveform that if you're restricted to a magnetron or a microwave oven, you can't do with. You can't do the things that we do with solid state with these other types of amplification ways that you amplify the energy. So it is a moment where we can take now a material, a device, a tiny little sort of thing that is minuscule in size, but it is applying to this new category of systems and this new category of technology, which EPIRUS, I feel, is out in the front of, and we're the leader of, but by no means will we be the only player here. This is too good of stuff to keep everybody out of and just say, hey, we're the market owner of this. Everyone else stay out. I mean, I do believe at a bigger level, this is an entire new branch of warfare, of electronic warfare, this high-powered type of mechanisms that we've been talking about today.
So, I mean, I've already admitted my total ignorance of these issues, so I don't feel bad then in asking the following question, which is gallium nitride, which I'm new to the existence of this material. Is this produced from commonly accessible, elements? Does it involve rare earths? What does the supply chain look like for something that you're describing as so important?
Yeah, there is. It's funny you should mention that. There's been a little bit in the news stuff about the substance called gallium, which is sort of like aluminum. Think of it as like aluminum or something. In fact, in aluminum mining is where you get gallium mostly from. But in China, they do sort of a lot of the world's production of gallium. In particular, with MACOM and our particular program, we don't source the gallium from China. So we made sure that we secured up our end of that supply chain piece. But it's a simple process. It just hasn't really been widely done because China hasn't tried to hold it over on anyone in the world up until recently. And now what they've done is, I think, created a lot of markets where in Canada and other places where they do a lot of aluminum mining, they're just going to start mining gallium alongside. So I don't think it's a difficult thing that they've got a world chokehold on by any stretch. They just up until now haven't been very sort of conservative about their export of it. And so I think folks have been using that. But a lot of the different things like solar panels that go into outer space, those are gallium arsenide based. There's a lot of different types of substances and systems that use gallium in a much more higher quantity than what we do. And so for our particular end of the spectrum of things you do with gallium nitride, we have a very easy supply chain that MACOM keeps in touch with, and it's all sort of local and well understood that we don't have any issues based on the defense nature of our business.
So we alluded sort of towards the start of our conversation that depending on the success of this technology, this actually creates problems not only for the bad guy drone swarms, but we are, as you put it well, I think me tooing. We are talking about building. I've heard them described as hedge forces, various kinds of drone swarms or cheap, attritable networks of systems of our own for the battlefield. So let's flip the map around. If technology like EPIRUS is successful at doing the job that it is setting out to do, how does the other side of this picture, whether it's the bad guys and their drone swarms or our own initiatives to do our own, high mass, high quantity, cheaper, attritable systems, how does that evolve to compete against this new countermeasure?
Well, it's what we talked about earlier in like electronic attack, electronic warfare, my old area of sort of work or focus at Raytheon. We always called it a cat and mouse game, where we would create a system with a certain, let's say, instantaneous frequency bandwidth, meaning it can jump anywhere at a certain frequency. And then they would create a radar with a wider instantaneous frequency band that they could go even further. And so then the electronic warfare system can't keep up. It can't catch where it's going. That's the cat and mouse that I'm talking about. And a lot of times in traditional electronic warfare, a lot of that can be software derived. They can update a radar system to do something different on the software side and create a problem for the electronic warfare systems. And if you look at NGJ, kind of my old baby, my back in the day, it was also created with a very software defined back end for this exact cat and mouse game that we're talking about. If you look at Leonidas, it's the same sort of an idea, or the same sort of idea towards the architecture, where our back end of our system is totally software defined in preparation of folks trying to do things like use copper tape or whatever to defeat our system. It's not really all that possible to do, because what we can do is then change the waveform to exploit new vulnerabilities in the way that you've just gone off and try to sort of kick us down or try to take the next advance. So let's think about this. On the drone side, the folks building the drones, they have to adapt the drones physically. They can't just go in and put some encryption in or something like that, like a traditional jammer system could do, or you could do against a traditional jamming system. You have to physically do something to help shield against some sort of a high energy like this. And then once you've done that thing, you've got to hope that I can, in my software end, just exploit that shielding as a vulnerability, making the shielding sort of your enemy by getting stuff in through it, through the penetrations and stuff like that come out to make sure that you have rotors, and different propellers and other things that come out of the body of the aircraft. I'm using those as vectors to get inside that shielding and then do even more havoc inside. So there's this cat and mouse game that will be played. Now, on the US side, now this is something very important. On the US side, I can work with my partners. I can work with AeroVironment and other folks that are doing the drones on our side. And I can create ways and methods that I will purposely make systems not be affected by what we do and allow those blue forces to operate in a high electromagnetic field, but we just tune it so that it won't tune towards their drones and we'll leave them alone. And that's something we've shown kind of on a commercial demonstration level. We've shown where we can put two drones of different types up next to each other, put the beam on both of them and drop one, but the other one stays flying. That's one method that we'll do. And then beyond that, it's just the coordination of FADC2 and the overall command and control to say, well, let's not, if we're going after an enemy, bunch of drones coming into attack and they're penetrated our defenses, let's make sure we're not flooding that same area with a bunch of good guys that were, and so there's two elements of it. One element would be to create systems that don't attack our system, but we'd have to do that in coordination with our fellow drone suppliers in the US. And then the other way to do it is just to not operate that way, either create a technological sort of notch in the frequencies or whatnot that cause those things to fly, or operationally just not create a situation or scenario where you have mixed forces like that, reds and blues in the same area.
Yeah, no, that makes sense. And I apologize. I may not have been totally clear in my question, but I'm sort of working on the assumption here that the success of your technology means that ultimately China, for example, will field something similar. And so it'll be a two-directional evolution in the the cat and mouse game, as you put it. Is there a way in which if the edge in this evolution, and I want to be respectful of your time here, so I'll make this my last question, but if the edge in this evolution remains on the side of the countermeasure, on the side of the defensive technology, does this just shift the onus of air attack back in the direction of something like ballistic missiles or things like that? Do you just have to go back to the more expensive stuff that's harder to drop out of the sky with something like this? Though I suppose that's an assumption. Can you drop missiles out of the sky with something like this because it'll mess with their guidance, or how does that work?
Well, it just all depends on how the systems are engineered and whether they've done a lot of thought around very, very high and complex electromagnetic interference environments. If they've made something that is designed to be very sort of robust against electromagnetic interference, it limits, basically what it turns to do is it limits our range quite significantly. And when you have high fast flyers and you have limited range, then it becomes sort of a point at which you say, well, without a lot of focusing of our energy or whatnot, maybe it's not the right technology to go after that particular threat. Now, I think there's a lot of in-between space where we'll see these very poor man ballistic missiles. They're like pipes, the body is like a pipe from a plumbing or whatnot, and they put nails and shrapnel in it, and they just send it on and it blows up. And those are very non-sophisticated systems that don't do a lot of thinking as far as how we engineer it, just to barely get it going. Those have susceptibilities for sure. And so we can look to those ways of defending with this sort of system. But for the most part, the amount of energy that we're putting out there will always have sort of a range limitation where we could probably one day talk about 10 kilometers. We could talk even about 15 kilometers. But I don't think we'll ever be talking about, unless I don't see the technology in 10 years of the future, but we won't ever be talking about 50 kilometers or 100 kilometers that we're putting this kind of intense electromagnetic interference and radiation in the air. Unless, of course, you go in another category of generating this stuff like the nuclear missiles and stuff that have the ability to do EMPs atmospherically. Beyond that, the way, kind of self-generating that kind of energy and putting it out into space, the air is very resistive. And so it knocks it down, the power down pretty quickly as it moves out from the source.
Andy Lowery, CEO of EPIRUS. This has been a genuinely fascinating conversation. I think we need to do more work here on this show, and non-engineers like myself need to do more work understanding how the technology itself is evolving. So I really appreciate you making the time. Thank you so much.
Thank you, Aaron. I really appreciate the invite once again. Thank you very much.
This is a Nebulous Media production. Find us wherever you get your podcasts.